Let's talk about German literature. If you want to talk about German literature, you need to understand something about German first. And you guessed it, if you want to talk about chemistry, you're going to need to learn something about the chemical nomenclature, how we name chemical compounds. So let's take a little bit of time and look at naming of chemical compounds. Oh, whoa, before you jump to the next tutorial, just bear with me for a moment. We'll make this as painless as possible. What we'll do is identify some of the most common names that you'll need to know. Go over those and try to point out trends where we can. There really is sense to how people name compounds, but the trick is sometimes finding it and finding those patterns. So let's take a little time and walk through some of the more common names and just highlight as much as we can what the patterns are. Okay? We're going to break this down into the naming of ionic compounds, the naming of molecules, and the naming of acids. Acids get their own special nomenclature, as it turns out. Now, as you recall, ionic compounds are divided into cations, positively charged ions, and anions, negatively charged ions. So let's start out with the cations. Okay? Now, for comparison, we'll look at the names of the elements, and this is actually very easy. For naming cations that are monatomic, it's very simple. We simply add the word ion after the name. So sodium plus becomes sodium ion. Potassium plus becomes potassium ion. Calcium ion. Strontium ion. Pretty simple, huh? Not so bad. Look at polyatomic ions. There are not too many polyatomic cations. The two that you are most likely to encounter in this course would be the ammonium ion or the hydronium ion. Ammonium, again, notice the IUM suffix in both of these. That's telling us that it's a cation. Okay? Now, let's go to the transition metal cations. Some examples here. A lot of the transition metal cations are going to be named just by referring to their normal name, but there are certainly some cations that unfortunately are named by their older name or their historical name. So in modern nomenclature, we would refer to the iron 2 plus cation as just iron 2. But the older style is to refer to it as the ferrous ion. Okay? Now, iron is one of these things that comes in a couple flavors. We also have an iron 3 plus cation. That's referred to as the iron 3 ion or the ferric ion. Okay? Notice the ending IC compared to OUS. We're going to see this again. The higher charge is accompanied by the IC suffix. Okay? So for instance, in copper, we have either copper 1 and copper 2, or cuprous and cupric. Again, notice the IC ending for the higher charge compared to cuprous. Okay? Tin, we have tin 2 or tin 4 cations. Those are referred to often in the older nomenclature as stannous and stannic. Once again, the OUS referring to the lower charge, the IC referring to the higher charge. Okay? And finally, mercury. Mercury comes in two flavors. There is the mercury 2 ion, and then look at this guy. This is two mercuries stuck together. Each mercury has a 1 plus charge associated with it, we could think of, and so this is referred to as mercury 1 ion. Okay? The old style, again, we call this mercurous or mercuric, depending on, again, whether we're talking about mercury 1 or mercury 2. Okay? Now, let's talk about anions. Okay? Once again, comparing this to the elemental name, chlorine as an anion becomes chloride, oxygen becomes oxide, nitrogen becomes nitride. Notice the IDE suffix. You've heard of the Ides of March? Has nothing to do with this. But it tells us that it's an anion. Okay? Other anions. Many anions turn out to be polyatomic, more than one atom involved. So let's look at a couple of these. Now it gets a little bit hairy. Nitrate and nitrite. Okay? Notice the ending, ATE becomes ITE when we lose one of the oxygens. Okay? Nitrate and nitrite are both used commonly as preservatives in foods. Okay? These are also called sometimes oxyanions, as you can imagine why they have high oxygen content. Sulfate and sulfite. Again, notice the only difference is sulfite is missing one of the oxygens. Okay? Also notice, by the way, that sulfate and nitrate, though they have the same suffix, don't have the same number of oxygens. That's okay. What's important is the relationship between these two, sulfate and sulfite, and these two, nitrate and nitrite. When we get into the halogen oxy anions, now we have more possibilities. We have perchlorate, chlorate, chlorite, hypochlorite. Okay? Perchlorate means one more oxygen. Hypochlorite means one fewer oxygen than chlorite. Okay? And chlorite is here for comparison, not a polyatomic anion. Okay, carbonate, the ATE ending again. Bicarbonate, ATE tells us it's an anion. Bi, that prefix tells us it's got a hydrogen. Okay, likewise, bisulfate is related to sulfate because of this hydrogen. One more hydrogen added to it. Acetate, cyanide, azide, these again are common names for ions. No rhyme or reason here, these are just historical names. Chromate and dichromate. The di refers to two chromiums. Okay? Notice the difference here. Bi refers to hydrogen, di refers to two. Okay? Okay, let's put all this together now and name an ionic compound. Let's look at this material. This is an example of copper 2 sulfate, okay, or cupric sulfate. All right? And notice that that name tells us that these should be considered grouped together. SO4, 2-, you recall, is sulfate. And so this overall comes as one anion, and the copper, again, is the cation for this. So copper 2 sulfate. Look at this guy here. This is iron 3 carbonate. Okay? Now notice that it's not diiron tricarbonate. There's no need for us to use those prefixes because we know the charge of carbonate is 2-. We know that it's iron 3, so we know what the combining ratio must be in order to have charges balanced. Must be 2 irons and 3 carbonates. So no prefixes are needed. Just ferric carbonate or iron 3 carbonate. Okay, let's talk about molecules. Now, these are nutrimolecules now, so we have a slightly different way of naming these. We're going to name these using the element that is furthest away from fluorine first. Okay, we'll understand why this is a little later, but for right now, that's a good rule of thumb. So CO is named carbon monoxide, or monooxide, and we just remove that oxygen. And we also could call this monocarbon monooxide, but again, normally people don't use that naming. Okay, CO2, carbon dioxide, SO3, sulfur trioxide, N2O4, dinitrogen tetraoxide. Notice again, this is not tetraoxide, but that A has been dropped and it's just tetroxide. Okay? This set of molecules has the property that when we dissolve the gas in water, it readily ionizes. So it's as if it's an ionic salt. So we name these like ionic compounds. HCl becomes hydrogen chloride, hydrogen iodide for HI, H2S is hydrogen sulfide. Again, notice that this is not dihydrogen sulfide. We're naming it as if they're ions, and so the ratio is known that there's going to be one sulfur or sulfide for every 2 hydrogens. Okay? Then there are some molecules that just go by their common names. H2O we all know is water, and you'd be pretty silly if you named this thing dihydrogen oxide. In fact, people would consider you a geek, so don't do it, all right? Ammonia is NH3, phosphine, PH3, nitrous oxide, N2O compared to nitric oxide. Again, notice the OUS versus the IC ending based on the ratio in this case of oxygen and nitrogen. Okay, the higher the amount of oxygen in the compound, that gets the higher, that gets the IC ending then. Okay. Finally, let's talk for a moment about acids and bases. Bases actually are very simple. We just name these as ionic materials. So sodium hydroxide, potassium hydroxide, calcium hydroxide. No need to use a dihydroxide here because, again, we know calcium is 2+, hydroxide is a -1, so it would be redundant to use those prefixes. This is just calcium hydroxide. Acids have, again, a unique naming system, a unique nomenclature to them. So let's see what's going on here. When nitrate anion is given a hydrogen, in other words, we talk about it being protonated to make this acid, this now becomes nitric acid. So notice what's happened. The ate suffix has been replaced by the ic, and we've added the word acid. Nitrite, on the other hand, the ite is replaced with ous, and again we get the word acid. So nitric becomes nitrous acid. Nitrite becomes nitrous acid. Sulfate becomes sulfuric acid. Sulfite becomes sulfurous acid. Okay, notice again, ite is replaced by ous. Okay, perchlorate becomes perchloric acid. Chlorate becomes chloric acid. Chlorite becomes chlorous acid, and hypochlorite becomes hypochlorous acid. Make sense? So, in general, we haven't covered but a tiny fraction of all the chemical compounds you're likely to encounter in your lifetime. But hopefully, with this sampling, you get an idea of what types of things people look at in considering how to name a compound, and hopefully you're learning enough about nomenclature as we go on that other unfamiliar compounds will start to make sense based on their chemical name. There's a lot of information involved in the chemical name. The prefixes tell us how many atoms we have oftentimes. They tell us about the relative amounts of some atoms compared to others. We talked about oxygen content, for instance. And as you learn more about nomenclature, more and more trends will emerge. So stick with it.